Last time we talked about polynomials and what we called rational functions. And rational functions are things that look like polynomial over polynomial. And so we didn't really get a chance to do a word problem involving that. So we should start there. So we have a company that makes snowboards. That sounds cool. In a given day, 20 boards are produced at a total cost of $3,800, of which $200 are fixed cost. And we have a bunch of things to do here. So part A. Assuming cost is a linear function of the number of boards, x, then give C of x. Now, there's a clue here. Linear. Well, okay, so that means that C of x has to have the form, ax plus b. So because it's linear, we know it has to have that. Now, we should try to think in terms of cost. Can we think about what b and a are? So let's maybe start with b. That might be the easier thing. What would b correspond to in this function? And you can, if you know a number, you can say a number, but if you also have a name, what's the name? Sorry, what? Well, it's the y-intercept, right, that's graphically. But in terms of this cost function, putting on our economics hat. Well, that's ax plus b, a slope-intercept form. But again, in terms of the cost function, be fixed cost, right? It's how much you'd have to pay even if you produce nothing. How do we know that? Plug in 0. That's you producing nothing. And what are you left with? B. So here, this portion is your fixed cost. You have to pay this regardless of how much you make. So then what is A? Okay, A is slope. That's if we think graphically. But thinking about it in terms of cost, how can we describe A? I'm not saying that there's an elegant answer necessarily, but what is that telling us? What information is A telling us? Okay, so it's like a variable cost. And I can think of this as like, cost of producing one item. Not, the variable cost I think is probably the right word. But, okay, you have the fixed costs, you took care of them. Now how much does it cost for you to make one? So let's think about our situation. Do we know what our fixed costs are? Yes. And the clue is, they told us. They said $200 are fixed cost. So that's cool. So we know it ends in a plus 200. Now the question is, how do we figure out that coefficient? How do we figure out what goes in the box? Well, what information do we have that we haven't touched yet? $3,800. Notice that's the total cost. That includes your fixed cost and your variable cost. And how many did we make? 20. So when we made 20, it cost us $3,800. So how do we use that? Well, we say let's plug in 20. So the cost of producing 20 is, we can come up here, it's like A times 20 plus 200, and that equals 3,800. Well, now we can start doing math and solving for what that coefficient we're after is. What's the A? What would we do? Okay, subtract 200, that would give us 20A equals 3,600. Divide. So A is 3,600 over 20. Nice thing about things that end with zeros is you can cancel zeros at the ends. 360 divided by 2, 180. So each snowboard has its own variable cost, as has been mentioned, of 180. And then there's a fixed cost of 200. All right. So that is the answer for A. So now, go to part B. Find the average cost function. Now, you might notice something that's written down. When they said the average cost function, they wrote this little bar on top. And this shows up frequently where when you see a bar on top, that's associated with an average of some sort. Okay, so average cost. So how does one compute the average cost? If I produced, well, let's just look at our problem here. We have 20 boards. It cost us $3,800 to make those 20 boards. What is the average cost per board? $190. Right, how'd you get that? Somewhere over on this side, I heard it. 190. You divide, okay. So you said, I know the cost. I know how many I made. So we can do some division. So the average cost, say, well, what's the cost? And divide by how much we made. Now for us, we know our cost function. So that becomes 180x plus 200 over x. And now you see, oh, this is why this connects to what we talked about last time. Upstairs, polynomial, 180x plus 200. Downstairs, polynomial, x. So this is a rational function. Now there's another way we can write this, because what we can do is we can take the denominator and put it under each term separately. So 180x over x plus 200 over x. Now sometimes it's useful to do this, sometimes it's not. But if we did that, what would we see? Well, the x's here cancel, so we get 180 plus 200 over x. Either form is great. They both represent the average cost function. Okay. Now it says sketch C bar of x. We're not going to be super precise. We're just going to get a rough sketch. Let's talk asymptotes. Do we have any, well, let's start horizontal. Are there any horizontal asymptotes? And if so, what is the horizontal asymptote? So two questions. Question one, is there a horizontal asymptote? Question two, what is the horizontal asymptote? So question one, is there a horizontal asymptote? Yes. What is it? Not zero. So how do you look? You can do it in two ways. If we have it in this form, 180x plus 200 over x, we can say, well, for large values of x, ignore the small stuff. What's the small stuff? Anything that's not attached to the largest power of x. So for large values of x, it really looks like 180x over x, also known as 180. If we write it in this form, we say, well, there's 180, and then we say, well, what's happening to 200 over x? 200 over x does what if x is big? Because horizontal asymptote says very big values of x. What's going to happen to the 200 over x? Gets small. You're left with 180. So we know a couple of things. There's a horizontal asymptote of 180. Do we have a vertical asymptote? So vertical asymptotes, where do we look? You look downstairs. Say, okay, could that ever be 0? Could be 0 at 0. So you have a vertical asymptote of x equals 0. Because, well, what happens? If you make nothing, well, you still had to pay the $200, but you made 0 product. So your average cost per product is ridiculously high. 200 divided by 0. So, what do we have? Well, if we plot, now one thing is we're not going to have negative x. We don't really care about negative values of x. Why don't we care about negative values of x? As a function, we can plug it in, but why don't we care about negative values of x?
Because they don't work. You can't have a negative number.
Yeah, you can't make a negative number of snowboards. You can't be like, I made negative 5 snowboards. Bring 5 snowboards in, and there's no snowboards left. You know, there's not the anti-snowboards out there. So it only makes sense to talk about what's going on for x greater than or equal to 0. We know we have a vertical asymptote of 180. There's no intercept for the x-axis, because 180x plus 200 equals 0 would be an intersection over in the negative value, so we don't care about that. We have a horizontal asymptote at 180. And we can say, well, what happens? If x is a small number, 180 plus 200 over a small number is going to be a big number, so it's coming off the vertical asymptote, and then it's going to approach the horizontal asymptote. So that's the sketch. And I think the main takeaway here is capture the vertical asymptote, capture that horizontal asymptote. Now our final question. Part D. What does the average cost per board tend to as production increases? So we're very successful. Right now we were just making 20 boards. Imagine 1,000,000 boards. Think big. What does our average cost go to? So your average cost function is here. What is your average cost going to? It's going to your horizontal asymptote. It's going to 180. Now, does that make sense? Well, let's think about it. When we think about our cost, there are 2 pieces. There's the fixed cost. Maybe that's like the cost to rent the factory, cost to oil the machinery, whatever it is. We pay that amount regardless of how many we make. And then there's the variable cost, the one which is attached to saying, well, how much does it cost to make each one? If you make a lot of units, each unit still costs you your variable cost per unit. But the fixed cost is now being spread more evenly. And so the more units you make, the fixed cost per unit is driving down. And so as production increases, this part here, this 200 over x, is going to go to a very small number. And so we're just going to head to 180. All right. Any questions on this one? Okay. Good. Well, our quote for the day, Fred Rogers, also known more popularly as Mr. Rogers, said, there is no normal life that is free of pain. It's the very wrestling with our problems that can be the impetus for our growth. And I think what I want to say, challenges are okay to have. Don't be upset that you have challenges. You are not going to live a normal life. We don't want you to do that. We want you to live an amazing life. And you're going to face hurdles and obstacles. Learning to deal with them will help you get better. And we want you to get better. Now, where are we going? What's our goal for today? We're going to talk about one of the most important functions that arises when it comes to financial situations, and that's the exponential function. Where does it get its name? Well, it's where the variable is. So now, instead of having like x to a power, now it's something to the x. So it's like the base to the x. And this shows up in many situations, in particular things like modeling growth and decay. And so it's useful to know. This is a typical sketch. We'll talk more about this in a minute. Now, where are we going to look at it? Well, we're going to look at compounded interest. So in other words, we'll start by thinking about, how does money grow? If you make an investment, you can expect some kind of return. And oftentimes you say, well, I want a certain percentage back. And so that's a multiplicative thing. You say, well, I want 5% back. Well, okay, how do you figure that out? It's like, well, it's your original investment plus an additional 5 is 1.05. So whenever you have that sort of multiplicative growth, that naturally leads to this type of having the variable upstairs in the exponent. All right, so a little bit about exponential functions. So again, where does it get the name? Well, because the variable is up in the exponent. So that's how we can remember it. Now, we're going to make some assumptions about what's downstairs. So when we talk about b to the power x, we're going to assume b is positive and assume that b is not 1. Now, why do we throw 1 out? Well, 1 is not a very interesting situation. If I say, well, let's look at the function 1 to the power x, what does that function look like? 1 to the x, what is it? What's 1 to a number, 1 to a power? It's 1. So 1 to the x is a flat line. That's not very interesting. So we'll assume b is not 1. We're also going to assume b is positive. Now, there are cases where we can take negative numbers to certain exponents, but the issue is that negative numbers to some exponents, like a negative number to the exponent of a half, gets complicated. And we're going to allow our exponents to be anything. So to avoid complication, we're always going to assume we're dealing with positive bases. So b is positive. Now, what will happen? If b is greater than 1, that's going to correspond to growth, and our exponential function does the following. We're going to cross b to the 0 is 1. And as we move to the right, so in other words, increasing values of the exponent, we're going to get larger. On the other hand, as we move to the left, so smaller values of the exponent, we're going to get smaller. But here's an important thing. The exponential functions will always stay positive. You can't get to 0. You can't get to negative values. So b to the x, always positive. So that's one of the things we say over here. Our domain, you can plug anything in you want, but our range will always be positive. On a side note, this is just a single value of b. You can plot other values of b, and what they'll tend to look like is you might look something like this, or maybe something like that. Okay, so I have some colors here. I have a red, a blue-green, and a purple. Let's see if we can reason out. Which one of these three colors, red, blue, green, or purple, which one has the highest value of b?
Red.
Red? Okay. How can we reason that out? I agree with you. Red is the correct answer.
Because it's slope.
So there's a couple things. One thing you can do is just plug in 1. What happens when you plug in 1? You get b to the power 1, which is b. So whatever you do when you plug 1 in, that tells you what's going in downstairs. So you can see that the purplish one is a very small value of b, while this blue-green is a little bit higher value of b, and then this one is a very high value of b. So when in doubt, if you're trying to figure out, oh, I have an exponential function, it's b to the x for something, if you have a graph and you know it's b to the x, you just say, well, what's happening at 1? Wherever you're at 1, that tells you your value of b. All right, so b greater than 1, that models the growth. If you have b between 0 and 1, that models decay. And so some classic examples that people often see deal with like radioactive decay. But you can also talk about other things. We talked about depreciation before. We had an example of a person who had bought a tractor. What happened to their investment? Depreciation is things go down. And a more realistic model in some cases is not straight line depreciation, but more of this sort of exponential depreciation. The idea is you lose the most at the very beginning, but then in the long run, it sort of stabilizes out. So there are situations where we want to model things between 0 and 1. So that's our decay. And you might say, if you look at these two pictures, they kind of look like mirror images. And well, there's actually a reason for that. So if you think of 2 to the x versus a half to the x, so suppose we looked at these two. 2 to the x versus a half to the x. So this first one is an example of growth. The second one is an example of decay. What's another way to write 1/2 to the power x? Well, of course, this is a very open-ended question because there's several ways you could rewrite it. I claim 1/2 you can think of as 2 to the minus 1. And so 1/2 to the x is 2 to the minus x. And you'll say, so the difference is there's a minus sign. And the effect of the minus sign, if you think about it, that's dealing with our input, and it's essentially saying, flip it over. So when you have that negative, it's flipping it this way. So that's why these two graphs will look mirror image. All right. There is a note here. exponentials grow quickly. And so if you were investing, in particular if you're investing for the long run, you're looking for an exponential growth and you want to get the highest value of B that you can. You might say, well, you have some investment choices. Maybe I get $1 a day every day for the next 30 years. And someone else comes and says, well, I can't give you $1 a day. But how about this? I'll give you 0.1% per day for 30 years. But you'll start with $1. Now, you might say, after a year, the $1 a day sounds pretty good. You get $365. 0.1% per day, I worked this out. You get $1.44 at the end of the year. After 30 years, if you did that $1 a day, you're a little over 10,000, almost close to 11,000. At that rate of 0.1% per day, you're up to 56,000. Exponential functions do really well in the long run. It's one of the reasons why they encourage you to invest in your retirement when you're young. Let exponential growth work for you. So hopefully you still have a few more years before you have to worry too much about that. First, get your diploma, then go get those great jobs. All right. Okay, a few other things. We do have horizontal asymptotes. Depending upon whether B is positive or negative, we're going to approach 0 in one direction. We have our basic rules for exponents, which we've talked about before, but we also have some other nice facts. We have that a to the x equals a to the y, if and only if x is y. Now, I should make a note that, again, we're not going to let 1 be an option here. And on the other hand, if we have b to the x is a to the x and x is non-zero, that tells us that a equals b. All right. Well, let's try some problems. Okay, if I can get the paper to come. Come on, paper, you can do it. There we go. All right. Here we go. Solve for x. So there's a couple of things. These are multiple problems. The first one, 2 to the power 2x plus 5 is equal to 2 to the power 101. What do we do? What do we do? Yeah, the 2's downstairs match. Since the 2's match, then we say, hey, that says we need the exponents to match. All right, so that gets us to a simpler problem. So we need 2x plus 5 equals 101. What do we do to solve for x? Start by subtracting 5 from both sides. 2x equals 96. And then divide by 2. So we get x equals 48. So in this case, one solution. Okay, well that was pretty straightforward. Let's see if we can't keep going. Our second problem, 5 to the power x squared minus x is equal to 25 to the power 21. Now, can we do what we just did? What did we just do before? We said, hey, let's make these match. Can we just say, oh, let's set x squared minus x equals 21, and off we go. Is that legal? No. Why not? Well, yeah, 25 is not 5. And so at this point, do we like No, we're not going to do that. We're not going to give up. 25 is not 5, but 25 and 5, they feel like they're connected. maybe there's something that connects these two quantities together. Can you think of anything that ties 25 and 5 together?
25 and 5 squared.
Aha, 25 is 5 squared. Okay, well, maybe that'll help us. So let's see. So we are allowed to rewrite things. So that we can write this as 5 squared to the 21. Is there another way to write 5 squared? Because I'm just replacing 25 by 5 squared. Is there another way to write 5 squared, all of that to the power of 21? Yeah, what do we do with these exponents? How do we combine? All right, we need to know our exponent rules. A power to a power becomes multiplication. 5 to the 42. It was written down on here. I didn't spend a lot of time because this is something we've mentioned before. But again, if you have a to the x to the y, a to the x times y. It's when you have a to the x times a to the y, that becomes a to the x plus y. So you want to make sure, know when you can add versus know when you can multiply. Now, what can we do? Okay, solve for x, but what do we need to do before we solve for x? All right. Just say now we can do our trick where we said, aha, since the downstairs pieces match, we have 5s in both cases, then we can set the upstairs. So we need x squared minus x equal 42. Ah, beautiful. Quadratics. We love quadratics. We've mastered the art of the quadratics. Move everything over to one side. X squared minus x minus 42 should be 0. Does this factor?
Yes.
Okay, someone told me yes, so I'm going to write it like it's factoring. And since we see x squared will be x and x, what else do we have? X minus 7 plus 6. We're looking for two things that multiply to negative 42 and add to minus x. Any way you get this is fine. If you like quadratic formula, that's great. We can also check x squared, good, plus 6x minus 7x is minus x, and minus 7 times 6 is minus 42. All right, now, that's not an answer, but we're much closer. We can now say, hey, I have two small problems. X minus 7, when is that 0? 7. X plus 6, when does that equal 0? Negative 6. And that gives us our answer. 7 or negative 6. So now this was one where we had two possibilities. All right. I'm going to skip the third one for a second. 2 to the power 3x minus 1 plus 2 equals 0. All right, how do we solve for x here?
Do the same thing, just 2 is 2 and 1.
So what do we do?
Just write 2 as 2 is the 1.
Sure, we can write 2 as 2 to the power 1. Now what? Okay, we could subtract the 2 over. Okay, or we write this as 2 to the power 3x minus 1 equals negative 2. All right. Oh, sorry, excuse me. Negative 2 to the power 1. Now what?
just negative 1? Or cumulative?
So you want 3x minus 1 to be negative 1?
No, 3x minus 1.
Is that the exponent sequel? I just want to make sure I understand our plan. There's a small catch, though. What do you do about this negative sign? As people might say, Do we know anything about exponential functions? We know of a few things. We just started learning about them. But is there anything in particular that we know about exponential functions? They're very optimistic functions, you might say. What? They can't be negative. They're always positive. They're always, there's an old song, always look on the bright side of life. That's the exponential functions. So, can I take 2 to something and get a negative number out? No. Can't be done. Wouldn't do it. So what does that tell us about our solutions? There's no solution. Not every equation has a solution. No solution. Exponential function can't be negative. All right. Okay. Now we'll do the last one. We skipped one of them. So we should do that one. 5x plus 18 to the power of 4 equals x plus 6 to the power of 4. And I think I grabbed this one from the book. And I'm not very happy with this problem being in this section. But since it made it in this section, we're going to talk about it. Okay. So 5x plus 18 to the power of 4 equals x plus 6 to the power of 4. What do we do? What do we do? We can do what? Did you say we should factor? Or somebody, it sounded like there was somebody over here. Here, it's the exponents are matching. So if the exponents are matching, sort of like, we're like, what should we do? What should we do? Well, what we should do is say, if the tops match, then the bottoms should match, right? Here we said, hey, if the bottoms are matching, the 2's, then the top should be matching. So this seems to be telling us that we should get 5x plus 18 equals x plus 6. This is going to give us a correct answer. I'm not saying this is wrong. What do we do from here? We can move things around. For example, we can subtract x, subtract 18. So that would give us 4x is negative 12, or x is negative 3. Okay. So, is that the whole story? Or is there more to be said? Because there's a suspiciously large box there, almost as if there's more to be said. Raised to the 4th, okay. So what's going on? This is, again, I'm not a big fan of this problem, but since they threw it in here, we have to talk about it. What's true about raising things to fourth powers? It'll always be positive. So the problem is you might lose a sign. So there's actually two scenarios. If the power were strictly an odd number, what we did is it. But when it's even, so we have since 4 is even, we have to recognize that maybe they're not exactly the same sign, but maybe they're opposite in sign. So this is why you run into some subtleties. So when you have an odd power upstairs, you don't need to worry about that. When you have an even power upstairs, you may say, maybe they're opposite in sign, so I have to check that scenario as well. So this is the same as saying 5x plus 18 equals minus x minus 6. And what do we do next? Well, same thing we just did. Move x around, move 18 around. So then we get 6x is equal to minus 24. Because I would add x to both sides. That's where we get the 6x. Subtract 18 from both sides. That's where we get negative 24. Or x would be negative 4. All right. So you get two possible solutions. So be careful. Be careful. All right. The other thing we want to talk about today. Oh, any questions? Sorry. Sometimes I just get so eager to move forward because the next one is going to be of interest. No, okay, no questions. All right. So we're going to talk about compounded interest. And there's two formulas. We're going to do the complicated formula, and then we're going to do the simple formula. So the complicated formula says, let's suppose you have an initial investment. So we're going to call that C. So C is your initial amount. And then there's an interest rate. And you say, well, that's my return on my investment. And we're going to put our return on investment per year. Like, a 5% return on investment per year. Now, of course, you say, well, naively, then, if I invested $100 at the end of the year, I should get an extra $5. But you start saying, I want to get a partial return on my investment sooner. So maybe I want to have not just once a year, but I want to get partial returns on a more frequent basis, maybe once per month, maybe once per week, once per minute. Why not? Okay, so how do we do that? Well, so the question we want is, how much do you have if you have your initial investment, C, you have your rate of return, or your interest rate, you invested for some number of years, T, and then M, well, that's how many times you're getting a return. So maybe you get it once a year, twice a year, 100 times a year. So what do? Well, first off, you say, okay, for any given period that I'm getting a rate of return, what I do is I multiply. So that's where this sort of exponential behavior is coming from. You get 1, which is your initial investment, plus that interest rate. But if you're doing it multiple times a year, you have to divide by M. Now what happens? Well, how many times do you get this multiplicative factor coming in? Well, M times T. Because you have M times a year, and you do it for T years. And so that's how many times you multiply, and that's what your cumulative interest rate becomes. Now we'll do a very special case. Suppose we're going to start with $1, $1, if you will. We're going to go for 1 year, and our rate of return is exceptional, 100%. Now the question, how much should we have after a year? Well, if we say, I'm only going to get my once a year, figured out my interest, well, 1 plus 1 over 1 to the 1. So I got 100% return, $2. But what if I said, no, I want it every month? Well, what happens then? Well, 1 plus 1 over 12, because m equals 12, to the 12, because I have to do it 12 months. Now, all of a sudden, I have $2.61. And you might ask the question, where did this 61 cents come from? So how are we earning more money? Well, the answer is we're earning interest on the interest. So the sooner we start getting interest, then that can build as well. So we're like, oh, idea. Instead of going once a month, we go once a week. So now our m is 52, so you get 1 plus 1 over 52 to the power of 52. I'm up to $2.69. You say, no, once a day. 1 plus 1 over 365 to 365. $2.71. You can do it once an hour. You can do it once a minute. And so the more you do it, the more you capture the behavior. And this helps solve a problem. We said, well, why stop? We should never stop, never stopping. So what happens? We can say, instead of doing it, in time increments, we'll do it what's called compounding continuously. So you are always earning money. And if you looked at the numbers that we were writing, they were converging to this really cool number called E, 2.71828. So if you compound continuously, then you say, what's your initial amount? Then you take E to the power R times T. And this is what's going to capture our behavior. And this function, by the way, is very important for what follows in the next 2 weeks. All right, we'll talk more about this next time.